So yeah, we're going to have to walk through pretty quickly. So yeah, let's get started. Who here has heard of strace before? Lovely. So you should be pretty familiar with this output. If you haven't heard about it before, strace is a tool that allows you to trace system calls in your process, and it's a really nice way to debug your running applications. Nice, good stuff. And this amazing diagram by Brandon Gregg shows all the different Linux utilities available to do introspection of your program and your operating system. And strace sits at the top left, like somewhere over there, where the system call interface bridges within your operating system. You've got all these other lovely tools available. And Brendan has this amazing post on strace, but he has this following quip, which is strace seems to be banned in France because it's a cracking tool. Now, why is any of this relevant? So I was giving a similar presentation in Paris a few months ago, and like I needed to use strace to debug something, and I didn't want to break the law because I'm a law-abiding citizen. So yeah, I wanted to figure out why this is actually the case. It turns out that strace has been used for like password hacking because if you run strace on your remote end, you can see the password in clear text because at one point you do need to transmit it to the server and it does need to decrypt it and check it. And yeah, but it turns out it was a bit of a joke. France hasn't banned strace, so all the French people rejoice. You can use strace in France. But if you do have any other quips like this, where a government has banned a particular tool for no particular reason, please shoot me an email. So yeah, thank you for having me, and thank you for Sainsbury's for hosting this event, and DevOps-Exchange for having me. Yeah, really great to be here. My name is Suhail. I am a platform engineer at Monzo. And what the platform team does is we build the foundations so that other engineers can focus on building a bank and not have to worry about running servers and managing databases and stuff like that. Monzo is a fully licensed and regulated bank in the UK. We have these really nice hot coral cards, and we have over 2.5 million customers. And our goal is to build a modern, tech-driven bank, make your money work for you. Yeah, and we have stickers at the end. So yeah, come grab me if you want a sticker. Top pitch right there. So yeah, our banking platform runs on Kubernetes on top of AWS. We use Kubernetes to provide all the underlying infrastructure. Kubernetes is great. You know, it manages handling of failures and like scheduling of particular replicas of your application. Our philosophy is no engineer should ever be paged if a node dies or becomes unavailable. If there's no customer impact, no engineer needs to be woken up. Now, some might say that we were running a bank on Kubernetes before it was cool to run a bank on Kubernetes. Now, let's talk. That's enough about banks for now. Let's talk about ice cream because ice cream is very appropriate in weather like this. Let's imagine that you're starting a company which is going to deliver ice cream to customers' homes and workplaces on demand. It's a great idea. You're going to make millions, especially on a day like this. I would sign up for sure. Like if you delivered ice cream to my workplace, if I was able to pick it up, Uber style, I'd definitely sign up, especially today. You start with an application, a simple one. You want to get up and running quickly. A monolith application, sure. It talks to a single database. You front it with a load balancer. Maybe you run it on AWS. Maybe you run a few instances with this application, for higher availability. This is your minimal viable application, and you get it up and running quickly. So you can focus on what really matters, which is delivering good ice cream. Your monolith app has all the things it needs to run your application. Everything from taking orders to making deliveries and managing inventory and providing great customer support. And your customers are really happy. Your business grows fast. You've sold out of ice cream all today, and the heat wave is coming. So your demand is getting higher and higher. You onboard more engineers, and it becomes more painful to manage release cycles of your application. Coordinating changes are hard. Rollout times are long. So you decide to split out your components into logical units based on function. And these services, they're going to want to talk to each other to share data and inform state. So what you do is you build APIs and interfaces between these services. You design these so they're context bound, and so you don't have leaky abstractions for your data. Each microservice is responsible for its particular set of data, and you don't want that stored across multiple places in different forms. Now, to achieve this in practice, there's going to be a lot of communication back and forth between these services. These services are going to communicate by not sharing memory. You're going to communicate via APIs and stuff like that. Now, at Monzo, we have 1,000 microservices, and each of these are bound to a specific context, a specific function. And this allows us to be flexible of scaling services on our platform, but also within our organization. As we've onboarded more and more engineers, and we've added more and more different logical units within our company, and restructured and grown, we've been able to assign these microservices to different logical units within our organization. Now, the predominant language at Monzo is Go. Go is excellent. It has fantastic libraries for concurrency and networking, all baked into the standard library, as well as fantastic third-party libraries as well. It's got a great ecosystem, but some teams might prefer to use other languages. For example, the data team uses Python because all the machine learning and all the data analysis tools are in Python. We don't want services written in Python or any other language to feel like second-class citizens. We want to build an agnostic platform. Now, even though Go is a great use case, our platform needs to be polyglot and language agnostic. We want the same RPC characteristics, no matter what language you're using. Now, when building an RPC layer, there's a few things we want to really optimize for. Services are going to be communicating often. We want a lot of capacity within our platform for services to communicate. So really need any sort of service proxy we have in between needs to be really highly performant. Now, this is the homepage of the Monzo app. You can view your balance and transaction activity right from the get-go as soon as you open the app. But under the hood, just to serve this page, more than 50 to 60 microservices need to get involved. And there's a whole bunch of things that happen after the fact, even after we've rendered this page, to do analysis and like auditing and logging and stuff like that. If we had a really slow service proxy in between, every single hop of those 50 to 60 services is going to compound and lead into a really slow experience. When you spend your card at a payment till, a whole bunch of services kick into gear to give an answer in real time whether you can spend that £1 on ice cream. Hopefully it's still £1 nowadays. This needs to happen within a strict amount of time. You don't want to be waiting. For example, let's say you go to Sainsbury's, and you don't want to be waiting at the till for hundreds of seconds while we decide whether you can pay for your meal deal. The customers behind you are going to get really, really angry. So once we've approved your payment, a bunch of other asynchronous stuff needs to kick in as well to let things know that, let you know that you spent your money. For example, you get this notification that you spent some money at Starbucks even before the receipt prints out in the till. And we can only achieve that by having a fast platform with fast RPC characteristics. Now, in a similar vein, services communicate often. And we want to support high throughput, but also high burstiness of traffic. You don't want your RPC system holding you back, especially when you're on peak load. Now, a replica of your service might become unhealthy. Someone ships a bug, you encounter a network issue, you have a glitch, a machine is about to terminate. An RPC layer should be able to detect that a particular downstream is not working as it is, maybe it's slightly slower, it's been hit by some bad networking, and try and root around this sort of failure as best as possible. Now, the RPC layer also has a ton of insight into how services in your platform are performing, and you want to expose this as an end user to people using your platform. So it'd be really nice if this RPC layer was embedded within your existing telemetry and tracing systems so that you can surface this information. Now, you take all of these requirements and you look at all the effort that you need to build a reliable and resilient system which is battle tested. It's going to be a tough task. Now compound that by developing it in multiple languages, and it's going to become practically impossible. Often you end up in scenarios where, even within the same language, you have different abstractions for achieving fault tolerance. And teasing this apart and seeing, okay, one particular system is using one version of one library, another system is using another version of another library is going to be impossible, especially when you're debugging, which is usually under when things go wrong. Now, a logic bug like this can have disastrous consequences. You end up in scenarios where you have a bug in the circuit breaking, for example, in one localized component, and that causes a thundering, cascading herd in your entire system. And unfortunately, that's how you get in the news, and not for the best reasons. And this is where a system like Envoy can help. So what is Envoy? Envoy's primary goal is making the network transparent to your applications. You send your request to Envoy Proxy and let it do the heavy lifting. It's a battle-hardened and tested service proxy. Now, service proxies and service meshes are not all that new. For example, if you've been working in Java, Hystrix, which is a library by Netflix, it was one of the first to encourage this service library service proxy style model, where you have a library embedded in your application, which is battle tested and resilient, developed by a core team, which has gone through all the failure scenarios, and has all the abstractions you need to handle network requests, and you just send your request through Hystrix. And so, yeah, this was Netflix's attempt to move away from each team having their own fault tolerance logic and circuit breaking, which could often lead to failures. Finagle is also a similar project with a similar vein. This one was developed by Twitter with a similar objective. It is protocol agnostic and asynchronous. It works well for asynchronous RPC, but also this is also a library that you embed. It's also Java based. But yeah, it also provides some really cool things like load balancing and failure detection. Now, both Hystrix and Finagle are developed on top of the JVM, and that helps in a large percentage of applications, especially if you're embedded within the Java ecosystem. But what if you're running Python or Go? Then you end up with a question like this, which is not a great situation to be in. It's very hard to embed Java in Go, unfortunately. So yeah, there was a service mesh called Linkerd2, which built on top of Finagle, which exposed Finagle as an external proxies that you can use within your applications outside of the JVM. Envoy follows a similar model. It has an out-of-process architecture. So this means it's completely language agnostic. You write your application, you send your request via locally running Envoy. So that means you embed Envoy, for example, as a sidecar, you put it in a known location, and your application doesn't even need to know, apart from proxying that request to Envoy, what happens beyond that fact. It gets to the other end. Envoy is written in C++, so that means it's fast and uses a low amount of resources. Not only because it's written in C++, because it's written in good C++ as well. The code is really readable and really understandable. And I don't class myself as a C++ developer, but yeah, it's really nice. Envoy has lots of configuration options, especially for load balancing. You could do your standard round robin. You could do weighted least requests or like hash ring based load balancing if you need, like, for example, some sort of consistent hashing where you have particular affinity to a particular replica based on your request. You can also set it to be zone aware so that requests are routed locally by preference, and you only go out if a particular local instance is not available. This really helps if you're in an environment like AWS, where cross-zone traffic costs money and local traffic is free. Envoy has great support for HTTP and HTTP2, gRPC and WebSockets as well. It can do the connection upgrading, so you can get a lot of the benefits of HTTP2 whilst having HTTP1 in your application, so that the middle layer, like Envoy to Envoy or Envoy to your downstream, can be upgraded to HTTP2, and you can get a lot of the latency and the binary protocol benefits and reduced head-of-line blocking and all the fancy stuff that HTTP2 has. You get a lot of flexibility when it comes to retries, timeouts, circuit breaking, rate limiting, and you can tune this for every downstream that Envoy is proxying. So you can say, oh, like service A has particular characteristics, you can't send more than 5 requests at once, so that means we'll rate limit it to 5 requests at any one time, where service B can handle millions of requests, so we can tune that to millions of requests. And you can do this all dynamically using your control plane, so you don't even need to restart your Envoy to change these options. And finally, Envoy has great support for stats and tracing. So you get a ton of telemetry on a per connection basis. So you can look at the full request lifecycle. They've now added a feature where you can tap into particular requests and you can see how requests are flowing through your system. You can see how long they took, when the connections got disconnected, and much more. And this really helps when you're debugging issues. A lot of this information would be really tough to expose in your particular application because you'd have to go low down in your network stack. So for example, let's say that you're using a system like Tornado in Python. You'd have to change a lot of Tornado internals to expose some of this information. Now, you're going to be hearing the phrases, especially when you look into service proxy and service meshes, about the data plane and the control plane. And what do we mean by that? So data plane is a component which is touching every packet in your system. It's the one that you put alongside your application, and it's the one that proxies the request. So this is what Envoy is. Envoy, it provides a data plane. You need to provide your own control plane. So the control plane is what provides configuration to the data plane. It's the component where you might front it with a web UI, or you might front it with some sort of configuration system where a canonical store of like all your downstreams. And this is the place where you can have like users tweak the load balancing settings and failure detection options and stuff like that within Envoy. Now, we're going to have to whiz through this really quickly because we are rapidly running out of time. But let's see how we can apply this in a realistic model. So here's two architectures that we have at Monzo. Let's go through those. So in this particular example, the order service here wants to talk to the account service. This is within a Kubernetes environment, but Envoy is not Kubernetes specific. You can run it outside and embed it with any sort of service discovery system. So each node here has an Envoy running on it at a known port. So to send any sort of request, you just talk to like a local host style system at port 4140 in this example, and you say route this request to the account service. The host here is service.account, and Envoy knows how to route that to a replica of service.account. Now, the question you might ask is, how does Envoy know? Where does the service discovery come from? How does it know to translate service.account into a canonical place on the other side? So we will touch upon that in just a sec. A node can have multiple different replicas running of different services running, and each of them can talk to the same Envoy. Because Envoy is fast and has great performance, you don't need to worry about a particular service completely overwhelming the local Envoy. It's not going to cause substantial degradation with your co-located replicas. But obviously, you should load test this in your environment. One of the other migrations we're doing right now is moving away from the local host-based model and running each Envoy as a sidecar. What we mean by this is each process, each application process within our environment runs a copy of Envoy. Which is very beneficial because then you can do a lot of network segregation. You can say this copy of Envoy can only talk to these other copies of Envoy in the downstream. So they're a lot more isolated. We also get consistent performance, which is nice to have. We talked about how would you do service discovery. Envoy is a data plane. You have to tell it how to route requests based on particular policies that you want. So Envoy provides a really rich set of APIs called the XDS APIs. And it's a set of discovery APIs which allow you to push changes and updates. So let's have a quick look at how that would look like in a Kubernetes world. So in a Kubernetes world, you might do watching based on service and endpoint updates. So for example, the Kubernetes metadata has services and endpoints that it keeps track of. It's basically a set of pods and a policy on how to access them. And a Kubernetes service will be backed by endpoints. So you can set up a persistent watch for this, watch for changes in endpoints. So when changes happen, your control plane will know that a particular change has happened in the environment. Let me push it out to all the envoys. Now, when your service discovery starts, it's going to need some initial state. You can just grab that from the Kubernetes API server. in your environment, let's say that you're not using Kubernetes, you can replace that with anything. You can replace that with console or etcd or whatever you use to store your service discovery systems. Now, everyone in the CNCF world loves YAML, and Envoy is no exception. Envoy has plenty of YAML. Fortunately, the amount of YAML you need to start with is very small. You just tell it where the configuration service lives, so your control plane that you've developed, which talks to your console or your etcd or your Kubernetes. You just tell it where that component lives, and it can pull the rest of the configuration. So, like on the Envoy side, Envoy will connect to this configuration service, and then from there you can have dynamic updates, which can tell how do I reach like service.account or any of the services in your platform. If you're using Go, there is some excellent support for writing an Envoy control plane and some excellent resources out there. You can use the Kubernetes client Go library, and Envoy has some fantastic Go libraries as well to write your own control plane. If you've not used Go before, this is a great way to get started. What this means is that this sort of service discovery is super flexible. You can do rolling updates, blue-green deployments, embed within your existing service discovery mechanisms like Zookeeper or Console or etcd with not a lot of effort. You can integrate that straight in. You don't need to completely rewrite your service discovery mechanism or run on Kubernetes to take benefit of Envoy. One of the philosophies within Envoy is that the service discovery is eventually consistent. So Envoy doesn't do service discovery in the path of routing requests. Cluster resolution happens in a background thread. So that means that not all the envoys will know about all the endpoint changes immediately. So that's something you need to take into account. You might want to do some better failure detection and that kind of stuff based on your Envoy configuration. But in practice, what we find is that they converge pretty quickly. If you think this is a bit hard, writing your own control plane, if you are in a Kubernetes environment, there is a fantastic project called Istio, which can provide a control plane out of the box. It also does a bunch of other things like mutual TLS. It does service discovery and more. So yeah, definitely look into that. You can also use Linkerd2, but Linkerd2 doesn't embed with Envoy. But yeah, if you need a service mesh, then Linkerd2 is a pretty good option. We're going to have to skip through some of these things. I do want to talk about this, which is load testing. So this is Bingo. Bingo is our office dog. And here he is after a hard day of load testing cardboard boxes. One of the key things that we did before we chose what we're going to have as our service proxy is get all of these spun up in our environments and run a bunch of load tests. This is standard practice to make sure that you're picking the right tool for the job. And what we wanted to do is we wanted to route requests exactly how they would be done in production. We actually ran some of these load tests in production, once we had Envoy rolled out to some of the fleet to make sure that it was performing better with no sort of service degradation. It was performing well under pressure. So we didn't find these things out at 3 in the morning. And we've actually found them out while we were awake and actively working on this. So yeah, HTTP is a really broad standard, and every single environment, including yours, will have subtleties about how it uses HTTP. You might have really long-running requests, you might have long polling, you might have WebSockets, you might not follow the spec. So yeah, definitely run these load tests in your environment and see how they actually perform. This space is super hot, so I've spent a bunch of time talking about Envoy. There's actually a bunch of projects in the works right now. We've talked about Envoy, we've talked about Istio. There's also Linkerd. So if you're looking for a fully fledged out-of-the-box Linkerd solution, service mesh solution, definitely check out Linkerd. Console is also having integrations with, developing integrations with Envoy, so definitely check that out. Finally, Monzo is hiring. So we are looking for platform engineers, backend engineers, iOS, Android web. So yeah, if you could grab myself, there's also Miles and Marcelo, somewhere in the audience. With a Monzo t-shirt. So yeah, definitely grab one of us. And thank you.
Again, we've gone slightly over, but we've probably got time for one or two quick questions. If anyone's got anything. I'm right at the back.
Hello. I wasn't quite sure what control plane you guys are using. I know you suggested a number, but which one are you guys using, or have you built your own?
So we've actually built our own control plane because we found that like a lot of the control planes seem to be quite opinionated about the Kubernetes environment, and we're quite opinionated about how we roll our own Kubernetes environment. Writing your own control plane doesn't sound isn't as daunting as it sounds. With a lot of the Go support, it's literally just plugging in two components. For us, it's Kubernetes and Envoy. And using these libraries is pretty easy, but it's given us a lot of flexibility down the line. We've written our own control plane. There's a bunch of examples on GitHub as well on how you can achieve this.
Oh, one more.
If you wanted to encrypt some of your comms, how would that fit into the picture?
So Envoy has great support for mutual TLS. The one caveat is you need to bring your own TLS solution. Something to issue certificates and wire it up correctly. So that would be embedded within your control plane, which you might custom write. If you don't want to custom write this, then Istio provides mutual TLS out of the box. You can hook into that.
Yeah, I understand after one of your outages you went for multiple clusters rather than a single huge one. What have you done to federate your service meshes?
Sorry, do you mean like putting Envoy as a sidecar on all of these components?
No, so rather than having a sort of Uber Kubernetes cluster,
yep.
I understood after one of your big outages, you broke your environment down into multiple clusters. So you must have a whole range of different service meshes supporting that. So how do you federate across those?
So last time I checked, which was just before this talk, Monzo still runs one Kubernetes cluster for all of its production data. So we don't have federated clusters. How would you use Envoy, across clusters, cross federation? So Envoy works pretty well as an API gateway as well. It can do cross communication between clusters. Obviously, there's latency implications, and you might want different configuration options. But yeah, that's something that we haven't really looked into because we just run one big cluster.